Let's discuss a question from theory of machine. This is a question from vibration. A small particle of mass m is attached to two highly tensioned wires as shown. The natural frequency for small vertical vibration if tension T in both wires is assumed to be constant is. So the tension T is assumed to be constant. Now you're asked what is the natural frequency for small vertical vibration. Now obviously because of the weight you can see that this will not be in this position because of the weight. Now because as it is you don't have any vertical force which balances the weight, so it has to come down, and as it comes down because the wires have tension, so because as it comes down it makes an inclination, so there will be some vertical component of the tensions which balances the weight. So in the static position, let's say it is something like this. So you have, this is let me just draw a good figure here. This is your reference line, so it has gone something like this in the static position, and let's say this deflection is delta and the tensions are T and T. So you have a weight that is acting mg. Okay, and let's say this angle is theta. So now in the static position I can say that the vertical component of each of the T is T sine theta, because this will be 90, this will be 90 minus theta. When you resolve this T, it will be T cos 90 minus theta, which will be T sine theta upwards. So 2T sine theta balances the weight. So this is in static deflection. Okay, and from this I can say that now if you just look at the system once more. So this is a static deflection. Now if you still further give a small vertical oscillation and leave it, so if you give a small vertical oscillation, what is happening is you are increasing the angle theta. From this what is happening is you are increasing the angle theta, and basically when you increase angle theta and T being constant, you are the 2T sine theta is increasing, right? So as it is, 2T sine theta balances mg, but if you further give small small vertical, if you just pull it if you just pull it by small amount downwards, basically mg remains constant because that's the weight. T also remains constant, but what happens is that as you pull downward, theta increases, and therefore as theta is increasing, sine theta will increase because it's in 0 to 90 range. So the vertical force increases, and when you leave that, the vertical force, the restoring force, is 2T sine theta, which is more than mg, and it brings it back. So this system is kind of the kind of like a spring, because in a spring what happens when you just stretch the mass and leave it, it goes back because the restoring force becomes more than your mg, and then it goes back, and then it goes, and that entire thing goes in a loop. So the same thing, why I compare this with a spring is because in a spring the elasticity provides a restoring force, and here the vertical component, which is 2T sine theta, the sine theta term provides the restoring force. Okay, so in static deflection, 2T sine theta. Now sine theta I can write delta, which is static deflection, by L. Now sine theta is nothing but opposite side by hypotenuse. Opposite is delta, and L is the length of the string. Okay, it's equal to mg. So the hypotenuse is same as the initial length, because now theta will be small, assuming that tension is very high. This L, this length and the hypotenuse length will be L, because theta is very small, and sine theta and theta are both same. So ultimately sine theta is delta by L. That is what is my point. Okay, And so delta, which is static deflection, so the static deflection is mg L by 2t. Now because this problem, see, one thing you need to recall is that most of the vibration problems, you can always convert them into a single spring mass damper and analyze. So here we have taken the static deflection from this given problem, and now if you take because this problem is equivalent to a spring mass problem, so if you consider the static deflection from there, mg is k delta and delta is mg by k. So from this you can say that this L by 2t acts as a role of stiffness. L by 2t acts as a 2t by L acts as a role of stiffness. So we can use the natural frequency formula which we use for our spring mass system. The natural frequency is root k by m, and comparing, so getting k, because ultimately this entire system we have replaced with a spring mass. Now imagine that the entire system is replaced with a spring mass damper with mass being the same and k being this 2t by L. So k will be 2t by L and mass will be m. So the natural frequency is 2t by ml. So this is one problem where you can always, this is one problem, but you have many such problems where a given system you have to always write down the equation in static equilibrium and then try to get a relation for the static deflection and compare with that of a spring mass static deflection. Okay, and when you compare with this, you will get a value for the spring constants, and that value basically means that when you replace your given system with a spring mass system, the value of k is what you get in the given problem parameters, and then you can apply the natural frequency for spring case. So remember this is because most of the complicated problem in natural frequency calculation, always you just need to just solve the static equilibrium equation and then just get the relation for static deflection as we did here, and then compare with the static deflection for a spring mass system, because the given problem is ideal to that. When you just stretch the mass m, the restoring force is increasing, and when you leave it, the restoring force become more than mg and it tries to bring it back. So there is similarity in equations, that's why you're using the natural frequency formula. Thank you.